Welcome everyone to the third webinar on the AI for Life and GloBIAS webinar series. Um, I wanted to quickly give a brief introduction of what is GloBIAS and what is AI for Life before we give space to the speakers. So GloBIAS, if you haven't heard of it, it's kind of a community and a society with more than 50 volunteers and 12 steering committee members and one community manager, here Krista present. With the goal basically of promoting knowledge sharing, fast networking, and professional development, advance tools and favor best practices for bioimage analysis, develop and share high quality educational resources for all skills levels, and tackle challenges and seize opportunities in the bioimage analysis field. It also regularly organizes events such as this one and also the second in-person conference that will be in Japan. It was initially supported by a grant by CZI and it's hosted by German Bioimaging and it's registered as a non-profit association. If you're interested in becoming an active member, either volunteering or an official member, you can go to globias.org and get all the information. AI for Life, on the other hand, is another kind of community with the goal of reducing the disparity between the theoretical applicability and the practical use of AI-based image analysis methods. So basically, as you can see from the image, it aims to bridge the life science community with the computer science community, which often has different, vocabulary and methods. If you want to know more about it, you can visit the AI for Life website at the link here. So today is the third seminar with the focus on building scalable and reproducible AI infrastructure for bioimaging. And today we will be hearing about Bioengine, which offers a user-friendly and cloud-based approach for serving and running bioimage models to models at your own institute. It was originally supposed to be presented by Wei Yang, which is this is a professor at KTH in Sweden and leading at the AI Cell Lab. But today we have Nils Mechtel, a PhD student in the same lab, presenting. And then in the second half, we will hear about the DL for MIC Everywhere, which tackles the challenge of reproducible and portable deep learning by containerizing interactive Jupyter notebooks for zero-code model training and inference. This will be presented by Iván Hidalgo Cenalmor, which is a PhD student in the Summer Migration Lab in Turku, Finland, and also the main developer of DL4Maker. So with that, I think I can stop the sharing screen. As a general for everyone, if you have questions, feel free to ask them. I think both speakers are okay with being quote unquote interrupted. We will try to aim at 20-25 minutes per speaker with a total amount of 1 hour. If you don't want to interrupt or you want to kind of leave the questions for later, you can also add them into the chat and I will make sure to follow up on it and ask the speakers as they go or at the end. All right. So I think, Nils, you can go first. You can try to share the screen.
Thank you, Marco.
Awesome.
This one, let me just move you away here a bit. Okay. Hi everyone from me, and thank you, Marco and Christoph, for having us here today and for the opportunity to tell you a bit about the Bioengine and how you can use it to serve models from the Bioimage Model Zoo, and how you can start your own Bioengine at your institute. As Marco already said, I'm Niels and a PhD student in Wei Yang's group at the Royal Institute of Technology in Stockholm, and we are located at SciLife Lab. I'll give you a very short introduction what SciLife Lab is and what we are doing there. It's a Swedish national center for life science research with multiple branches throughout the country. And within SciLife Lab, we are part of the data-driven life science program, and we're working a lot on bioimage analysis tools, developing them. And this program, this data-driven life science program, recently got another round of funding for the Alpha Initiative, which is an AI pilot project for with the goal of simulating cells, and led by Jan Ellenberg. It also has a very strong focus on bioimaging data, just as a background here. So let's continue with AI4Life. Marco already mentioned it. It's a community effort around the bioimage model zoo, what you can see here on the right, the website. And besides the model file standards and this repository for sharing those deep learning models for bioimage analysis, it also comes with a cloud-based model serving and test run. And this is what I'm going to talk about today. So if you go to the website and click on one of those model cards, here we can it looks like this if you click it, and then it comes with this description, as I just mentioned, with how the training was done, what the training data is, how to validate, and so on. But it also has a test run feature. So you open this here, and then this window pops up. You can click Run Model. This will initiate an image.js session. We have this example image. You click Run Model, and it will send it to the Bioengine. The Bioengine will run the model, and then will send back the result to you. And here you can even do some easy image analysis. You can also drag and drop your own image. So you can try it out before committing to it and downloading the whole model. How this works is in the front, you see the website, but behind that, you have cloud infrastructure that will serve the models from the Bioimage Model Zoo to you as a scientist, as a user here. And this is being done using the Bioengine and based on the HiFi technology. It's currently doing model serving and test run, but also validation and conversion during the uploading process. And soon this will also include training and fine-tuning of those models directly in the cloud and controlled from the website. So this is, I'll now tell you a bit how the Bioengine works and also how HiFi works, only very briefly. Feel free to ask more about it if you have more questions. But it has some main components. So we have the Bioimage Model Zoo repository here, and so all of this up here is the Bioengine. We have a Triton inference server that is pulling those models from the Bioimage Model Zoo, running the inference in the different given environment. And then we have the HiFi, which is a tool for connecting different clients remotely. And HiFi will allow the different clients. We have the Bioimage Model Zoo website here, but we also have different community partners, desktop clients that can consume those models, and also web clients like ImJoy and JupyterLite. I'll later use JupyterLite to give a quick demo how that works. Yes, so we used to use Triton Inference. Now we use Ray, and this has a simple reason because Triton Inference Server is very nice, but it only. And if we want to go from just inference to also training and fine-tuning, then Ray is a very nice framework. And as a motivation here, this ChatGPT or the GPT model behind ChatGPT has been trained using Ray. So this is a very scalable framework for training large models here. And this is what we are now using. And so Ray can run in different environments, different cloud providers, but also on a workstation, for example. And it has this key part in the core of Ray, this Ray serve. And this is what we are using to serve models from the Bioimage Model Zoo. And it also has is very well integrated into existing libraries like PyTorch or TensorFlow, and many others as well. So this is why we use this framework for distributing Python applications here. And HiFi is this tool for connecting different clients, as I mentioned. And the key part of HiFi is the server. So the server in HiFi uses Fast API to create WebSockets. It has some scalable vector storage inside for internal communication, and also has an object storage. And this object storage for Bioengine is the Bioimage Model Zoo, where we have the different models, and those are our storage, is our data in the S3 storage. And we use SQL to navigate this storage. And then HiFi server will start WebSockets to different clients For Python and JavaScript, this can directly be a WebSocket, but you can also access this just from HTTP API, using HTTP API, so basically from everywhere where you have internet access. And those WebSockets, they allow for bidirectional remote procedure calls. So a client here or like HTTP client here, they have in the browser, for example, or JavaScript here, you can call through the Hi-5 server a different client where you can run models in Python environment, and then send the result back to you so they can communicate back and forth with each other. And all of those, they have unique service IDs, so you can uniquely identify which service you currently want to call. As I mentioned before, we had the Triton inference server, and now we're switching to Ray as a backend here. And Hi-5 also comes with very fine-grained user access control in virtual workspaces. So you can have public services like on the Bioimage Model Zoo website, but you can also make it private and only allow specific users. So if you combine this, then you have the Bioengine, and you have this API with WebSocket and HTTP, as I just mentioned, where you can connect the website and different community partners' desktop tools. And the Bioengine will act as a central server to do so. So here are some community partners in AI4Life that use Bioengine and use the Hi-5 technology to consume those models. We have the website, but we also have the Bioimage.io chatbot. We have the Jupyter notebooks you can connect to it, but also to the community softwares, IC, Napari, and so on. Just to give you an impression where it is used already. And I want to show you that it's also used in the chatbot. So here we have the pre-recorded video of the Bioimage.io chatbot for segmenting an image using CellPose. And we are here in a very lightweight browser environment, so we would not be able to run a deep learning model here. But the chatbot is able to do so because it can connect to the Bioengine and run the model remotely in the cloud. I will skip a bit forward here. So here we can see it returns the segmented image in the chatbot. It sends the user mounts an image to the chatbot, and then the chatbot can segment it for you with CellPose here. Just as an example, that is a very versatile way you can use it. But let's cycle back to the title. It says you can start a Bioengine at your own institute, and it supports different modes. You can run the Bioengine very locally on your desktop using Docker or Aptainer, Singularity, or Podman. All of that is supported. You can also run Bioengine on an HPC, where it will schedule, like submit Slurm jobs to schedule new workers to be added to this Ray cluster. And you can also start it on Kubernetes or a different cloud provider. So you have the possibility to run it on premises for better confidentiality, or you can start it on a public cloud if you scale it more, depending on your institute's infrastructure. So now I want to show you how you can give you a demo how you can deploy and start a Bioengine yourself. And to do so, you need to go to this website, dev.bioimage.io. This is the new Bioimage.io website. This will be launched soon, so then it will be available on the Bioimage.io as you know it. Let me just stop here and move this in. So if you go to the website, you'll land here, and you can still see it, right? The screen, yeah. So then, if you click on applications, you'll have this launch Bioengine, and here this is a Bioengine that I already started before to make the demo a bit quicker, but you can click here for configuring your own Bioengine. Let's say I'm running on Mac OS. I want to use Docker here. I use two CPUs. I don't have a GPU on my laptop. So this is the default configuration that I'm using. There's also HPC option, or if you're connecting to a Kubernetes cluster on the cloud. And yeah, so this is my settings that I use. Then I can just copy this, and let me just move in the command tool here. I'll just copy and paste, press enter, and yeah. So then it starts. I need to log in, so I'll just copy this link here. It's logging in with my Hypha account. Let's go back to command line here. So you'll start see the Bioengine is starting first array cluster, and this will not take long, so just a few seconds. And now it's connecting to the array cluster. And now we have the Bioengine started. So let's go back to our user interface here. Can close that here. And it will already go down. You see now we have two Bioengine workers because I just started a new one. I think this one is the one that I just started. So I can click here and I will see some information, uptime, just something like 40 seconds when I started the service. We have a cluster here, and this service is what I mentioned with the unique service ID. So I can use this service here to interact with this, the Bioengine from a website, and this will communicate with the Python environment. And this is the CPUs that I specified is zero usage, 100% availability, because I haven't started anything yet. No GPUs, and yeah, so I have one worker node because it's just single machine here. So here we can scroll down. We have some available apps, and scroll down, and then we have the model runner from Bioimaging. And here we just choose CPU or GPU. I don't have a GPU, so I'll choose CPU and click deploy. And then we can see that this is now here deploying to this local Bioengine worker. To not let you just wait for just until this is installing the runtime environment, I will switch to the other Bioengine worker that I started in advance. And here I had 4 CPUs, and I already deployed the model runner. So here you see it's running. It's one replica. You can also scale this up, and it's just using one CPU. You can also use GPU. It might be a bit faster then. Yeah, let's go to the tutorial. Can just click here, and it will open Jupyter Lite, as I mentioned earlier. And yes, overwrite. Okay, so first, this is a tutorial and guides you through how you can use the Bioengine. I chose just any random model here, just the discrete rooster, the animal nickname of one of the models in Bioimage Model Zoo. Okay, this is initializing this session here. That should be done any second. And then I will run the unit as membrane for membrane segmentation using the Bioengine. To do so, I'll first download an example image. Let's run this, and then we will need to connect to the Hypha server to be able to communicate to the Bioengine. I don't know why this is not loading here. Maybe let me close this. I have it here. So this is already connected. So here. Discrete rooster, we have it loading the example image. We have it here. And then I'll connect to Hypha, same URL. Not the same, different key, but same base URL here for connecting to Hypha. Now I'm connected, and I want to use the public Bioengine. I want to use my own Bioengine. and this is the one that you just saw. If you wanted this, the client and that we had before. Okay, let's check the RDF. This is the model description file of the model ID that we pass here, and we can read that the model discrete rooster is a pancreatic phase contrast cell segmentation, has some description for deep image J, compatible, and so on. We also somewhere we see the input, what is expected here. So if we use that description, we can make sure that the image is in a valid shape. I'll just this depends a bit on the model that you're using, but its information is in the RDF file. And then now we can make a prediction. So what is this doing now? I'm sending the image from this notebook to the Bioengine, and then the Bioengine will send the result back, and we see that the prediction has this dimension. This because I opened it a second time. Let's visualize the outcome. And so now this is our input image, and this is our predicted mask. And this is how easy you can run a model from the Bioimage Model Zoo. If you want to run a different model, you can just change this model ID that you can get from the Bioimage Model Zoo, and then get any image, make sure it's in the right format, and there you go. This is how you can run models from the Bioimage Model Zoo using the model runner deployment in Bioengine. How am I doing with the time? 24, 22. Okay.
Yeah, I think we can go until 30 if there are a couple of questions.
Okay, good. So I will also share the slides later on, and there are some screenshots in the slides here how you can that will guide you through the steps how to run a Bioimage. A Bioengine worker yourself. So you go to the wizard, choose the Bioengine worker that you just launched, and then click model runner and deploy. And then you can open the tutorial as I just showed you. So before I'm wrapping this up, I will also want to show you a application that we are building using the Bioengine, and this is a collaborative platform for image annotation. Let's switch back to presenter mode again here. That's better. This is a human-in-the-loop collaborative image annotation platform that we're building, and it includes the Bioengine. Let me just laser pointer here. So we have the Bioimage.io model zoo, and we have the Bioengine as very key components here. And this application, you start with just raw images or pre-processed images, and you want to make a first prediction with a selected model from the zoo. So you do model inference from the Bioengine, and because you want to fine-tune this on your own data, you get a not optimal prediction yet, but this is where the human review comes in. So you can crowdsource annotation correction by humans, so they can correct the different the annotation here. I'll also show you how that works using the help of an AI in the loop, and then you can send this data to generate annotated data, and the data owner that has the data can collect those annotations and send those to the Bioengine in near future to do model fine-tuning. And so then you have an updated fine-tuned model that you can push to the Bioimage.io, the Bioimage Model Zoo. And then you can enter a new round. So in every round, you collect more and better annotations with the human review. The review needs to be less and less every round because the model gets better. So what you collect in this process is annotated images and also find different versions of fine-tuned models here. And this cycle goes infinite. You can always feed more data in and just endless learning or active learning of the model. How this works is also we have the bioengine as a key component here. We are using microsam based on like segment anything from Facebook, but trained on microscopy images. There should be citation somewhere. There it's from Konstantin Pape from University Göttingen, Germany, and yeah, you can run the interactive segmentation with microsam. You also have a data provider that provides the data, and you have there's annotators that can interactively annotate those images. Each annotator gets an image, interactive segmentation, then send it back to the data provider. Let me very quickly show how this looks like. So you, where is it? So you start the, sorry, one moment. Yeah. So you start this annotation session. Since we're a bit short on time, I'll just show you how the annotation looks. So you'll end up in an interface like this, and then you can just go here, click. You could theoretically just annotate yourself. On a mouse pad, this is a bit difficult. If you want to do automated segmentation, just click here and you use, depending where you click, you get different qualities of segmentation here. So this is where the human review then is also good to have. So yeah, just as a demonstration here. So if you combine all of that, you have and look at AI4Life, then the Bioengine is a very central component because it connects the AI model hub, it connects the different community partners, analysis tools. Also, the Bioimage archive is a data repository that I haven't mentioned so far, and the Bioimage.io chatbot. And with the wizard that I showed you, you can bring all of that to your own institute and run this locally. Yeah, thank you for listening. And again, thank you for inviting me here. Big thanks also to my lab, the AI Cell Lab and Wei Young, and of course the AI4Life community. Always nice to work in this community. Yeah. Are there any questions?
Thank you, Nils. We have a couple of minutes for questions, so you can either jump in or you can also write them in the chat. I can read them out loud.
I have a question.
Yeah.
Yeah, go ahead.
I was wondering in your bioimage engine,
Mhm.
so are these like the traditional computer vision models, or do you also support like these vision language models?
Yeah, good question. So the bioengine itself is not limited to any deployment. So it's built for just making deploying and serving and also fine-tuning training models easier and more accessible. The model runner deployment that I showed you from Bioimage.io, this is only consuming models from the Bioimage Model Zoo. But you can write your own deployment, and this is also meant as a let me stop this here. If you go to the Bioimage Model Zoo, you have models here, but you also have applications. So this is meant to grow. We have some community partners here, but we will also have those Bioengine apps here under applications. So the more the applications are developed, the more versatile this is going to be. At the moment, we have the model runner for Bioimage.io models, and also there's a cell post fine-tuning deployment that is being used in this workflow here. Where is it? Here. So you use cell post in the cell post fine-tuning process here. But you could serve any vision model. Just need to write your own deployment file for that, and this is pretty straightforward to do so.
We have another question in chat, so maybe we can jump to that. Omar is asking, well, it says, first of all, thank you, very impressive. Do you have a roadmap for like some of the other applications? He's referring specifically to Suppose Sam. I don't know if that already exists, Suppose 4 model already on the my Bioimage Zoo. But I also wanted to jump in on that. Maybe do you have like a timeline, for example, for this human in the loop and also like the new website and like kind of this new apps that you teased today?
Um, yeah, so I'm not the only one involved in that, of course. So for the model zoo, I'm not sure when this is going to be switched from the dev branch to the main branch. Um, for the fine-tuning and training of Bioimage Model Zoo models, at the moment we're relying on the Bioimage IO core library. So as soon as this library supports that, this will be very easy to include. In the meantime, I'm developing those BioEngine apps, and this is like microsam at the moment inference, but I'm also planning to do this for training. Probably end of this summer we will have more, or by the end of this year, I would say, latest have this workflow here. With more models and the fine tuning and maybe more universal for fine tuning, if that answers the question.
Right. Thanks a lot, Nils. Maybe you can, there's a follow-up question you can maybe answer on the chat meanwhile we move to Ivan.
Of course.
Thank you, everyone.
Okay. Sir. Okay. Oops. Like that. Present. Okay. Like that?
Yep.
Or
yeah.
okay.
It's yeah.
Okay. So hello everyone. Thank you for having me here. As I was presented, my name is Iván Hidalgo Cenalmor. And today I will be presenting here Deep Learning for Make Everywhere, which was a project that I developed in my previous group in Ricardo Enriquez lab. Deep Learning for Make Everywhere, in the end, is a platform that facilitates reproducible and portable deep learning for both, for developers who have a pipeline in a Jupyter notebook to be able to make it reproducible, but also for non-expert users that want to use these notebooks in a reproducible way. So the goal is to have these two users in deep learning for Make Everywhere. And I want to start the presentation discussing a little bit the reproducibility issues that exist nowadays in computer science. It's true that these reproducibility issues do not exist in all the programming language. They are more related with Python, but Python is one of the most programming language in research, and it's really nice because it's open source and it has a really nice community that is constantly contributing. But then it comes the problem of, okay, when you develop a project, you use different libraries, different packages, and each one has its own version. And here it comes the problem because there might be some conflicts between versions, and at the end, having a stable environment that you can work on, it's maybe not straightforward. And then it comes the next step. If you want another person to be able to use that your project and to be able to reproduce that environment is also something that many times it gets complicated, and it can be complicated when you want your colleague to test your program, or it can be complicated. It can has reproducibility issues when you in your future want to test something that you developed years ago, or even like it is here in this doodle where even between different operative systems, the same environment might crash in some of them. And nowadays, people is coming with different solutions. You can have a requirement list with all the libraries with the specified versions that you have. You can have conda environments, but from my point of view, the one that gives the best reproducibility and that is more stable is the containerization method. As a similarity, a containerization method is like a virtual machine, which at the end is a virtual computer inside your physical computer. And among the different containerization methods, I will say that the most known one is Docker, which, as I say, is, let's say that is like a virtual machine, these containers that are in Docker. But the cool part is that you have this Docker file, which is a template where you are able to define all the steps that you use. So this allows you to customize this virtual machine in as many ways as possible. So you can define the operative system, the Python version that you want, and inside Python, all the different packages that you want to have, so that you have everything wrapped up and that it works by itself. It doesn't need anything additional. And also, a cool part is that as it works by itself, it also works then in different operative system. If you have Mac, Linux, Windows, it perfectly runs. And if it, as it is frozen, it will also be able to be reproducible in a long term. Additionally, Docker is part of this open container initiative, which I think that is really cool, because at the end, if you have this Docker file, this recipe that I was mentioning, you will end up having all the steps that you use to create this container. This allows you to check that no malware, no virus is introduced, so you are really safe to install this thing on your computer. So I think that is gives some safety to the user. And I know that many of these terms might be a little bit complicated, so that's why I wrote this focal plane blog post. So if you have time to and you're interested in this topic, I would recommend you to give a quick read, because there I try to explain them, let's say, more user-friendly. So yeah, at the end, in Deep Learning for Make Everywhere, we use Docker as a containerization system, so that it takes your notebook with all the dependencies and is able to reproduce the deep learning pipeline, so that your colleague is able to have it in the same conditions, or even yourself. It will give you a long-term reproducibility. So if you develop a tool during your PhD, then while you are as a postdoc, that you are still able to use it. And I know that this containerization thing, it might be overwhelming for non-computer science, not computer scientist, but also even for the computer scientist, it might take some months to get comfortable using these things. So here, from the method contributor parts, we wanted to make this process much more simple. So the way that we did it is, when you have developed your really nice notebook and you have all the dependencies listed, when contributing to Deep Learning for Make Everywhere, we will take care of automatically containerizing it. So taking everything and putting in this container, in this box that I was telling you, so that you don't need to deal with this process. And additionally, the goal is that if everything goes right, because it will go through some validation, and if it passes all the checks, it will be automatically uploaded to Docker Hub. Which is the cloud storage system that Docker has. So your container will remain there in the cloud forever. And this has a nice additional feature, because imagine that you use TensorFlow to train your model in your notebook. You contribute, you create this container, and it's uploaded to Docker Hub, to the cloud. Imagine that in some case, TensorFlow suddenly removes all its libraries from Conda or from PyPy, and you can no longer install them. Still, the TensorFlow that is inside the container, it will remain. So even if it is not available anywhere, it will have it inside. So in 10 years, if TensorFlow is not longer available to install, it will remain here in the container. So you will still be able to use it. And I think that gives some security when developing a tools, and I think that is a nice feature. How can you contribute to Deep Learning for Make Everywhere? Imagine that you have the notebook. How can you access to this automatic containerization? So we try to do it in the simplest way possible. You just need to contribute to the Deep Learning for Mic Everywhere GitHub repository with this configuration YAML file and in it you need to specify some details. Most of them, they are versioning to have everything as well established as possible, like Python versioning, Ubuntu version, and for the GPU, the CUDA and the cuDNN. Then, to give some context to your container, you could have the description, the name of the image that you will have. But the most important ones are the notebook URL. This is to point where your notebook is, and the same for the requirements. You could have them in the Deep Learning for Mic Everywhere GitHub collection, but if you still want to have control of your notebook and you want to have it in your own GitHub repository, that's also possible. So you just need to point to your GitHub repository and it will still work that way. And the last thing is the notebook version. This is important for retrocompatibility because you ideally will continue developing that notebook, and ideally people will use the latest version. But imagine that some user used instead of the 1.6, it used for its research, its paper, the 1.4. That person will still want to remain using that version, and having this version in here allows that. So that I think that is quite important. Additionally, this configuration YAML file follows the specs from the Bioimage Model 2, and this makes it compatible and allows it to live in the same environment as well, it will be not in the models collection of the Bioimage Model 2, it will be in the tools, because at the end a notebook is the tool, but it will allow by automatic also uploading to have your notebook as a possible tool in the Bioimage Model 2. And yeah, you will need to add additional information so that it's there in the Bioimage Model 2, such as the authors, some citations, some badges, but everything is really compatible to work in both in Deep Learning for Mic Everywhere and in the Bioimage Model 2, which will give some visibility. So if you have developed your notebook and is automatically uploaded to the Bioimage Model 2, it will give some visibility to it, and it will let people that use the Bioimage Model 2 know that your notebook exists, and it will let them play with it, which is always nice. And then from the user's point of view, the way that they will access is by going to Deep Learning for Mic Everywhere, and it will automatically take it from the Docker Hub, from the cloud, and it will open it for you in your browser. All these things that I was mentioning all the time that they were doing automatic, the containerization, the checking, the uploading to Docker Hub, is done using the continuous integration system provided by GitHub, the GitHub Actions. The way that it works is that, okay, when someone contributes with this configuration YAML that I was mentioning, it will go check in different steps. It will check that it's a reproducible format, that you can actually build a Docker image with it, that everything is right. And at the end, it will check that it works, as I was saying, in different operative systems, in Linux, Windows, or Mac. So it's really reproducible in all the possible scenarios. So once all those things are checked, it will take it and upload it, as I was mentioning, to Docker Hub and the Bioimage Model 2. So it's accessible through different platforms. So now, from the user's point of view, how is this done? How have we tried to have it as user-friendly as possible? So we did it with a one-click executable. Now we will have a demo where you just have one file, you double-click, it will check if you have Docker installed or other softwares that you need. And if not, it will install it for you. And once everything is installed, it will pop up this graphical user interface where you just need to choose the notebook that you want to use, the path where you have your data for training or using your notebook, and where do you want to save your results. Then if you have GPU, you can choose to use it or not. And then by clicking run, it will take care of taking it from Docker Hub or building this Docker image locally. And at the end, what you would end up getting is in your browser, the Jupyter Notebook in Jupyter Lab. And here we have tried to remain as close as possible to the zero cost deep learning for MIC principles. This is no code, like the code is there, but the user doesn't need to write any code, so everything is hidden. You just need to interact with some widgets to put the path to your data, the number of training epochs, or whatever, that things are actually safe on your computer. So trying to keep the same experience that you have in Google Colab with zero cost deep learning for MIC. And additionally, we have made deep learning for MIC everywhere to be cross-platform compatible so that you can run it locally here, for example, that I will run now in my laptop, but you can run it in Azure in a cloud computing system, or if you have a nice workstation on your facility with some GPU, that you're also able to benefit from that. And you can still remain running it in Google Colab. So now, because this is everything screenshots, let's go to the demo time and check how it's done in live. So here it's, well, I can open it in deep learning for MIC everywhere here. So you just need to go to the GitHub repository if it loads. Okay, now, yeah. And here you will need to download, for example, here the repository, or you can do it with git clone, whatever you feel more comfortable with. Also want to mention that we work quite hardly in the documentation, and all these steps that I will talking about and that you will see, they are really well documented. Yeah, you can see here with the steps, step-by-step guides, or you can see all the YouTube videos that we have so that the process is easier for you. So here, once you download the code, you will end up getting here all the repository, and here you will have a different launcher for each operative system, one for Linux, another one for Mac, and in my case that I'm using Windows, I have this launcher. You just need to double click it. Yeah, it will take care to check if everything is installed. If not, as I was saying, it will install it for you. And at the end, you will get that getting this graphical user interface. Here, as I was saying, you need to choose from zero cost. I will be using the 2D unit in this case. Then you need to choose where do you have your data. For example, for me, I have it here. GloBIAS webinar data. Okay. And the results, I want to store them here. I already did some tests, so there are some cool models, cool units. But if you have already run it, you have also these load preview settings that speeds up the process. Then by clicking run, it will check to also be more efficient if you already have an image to use that and make it faster, or you can build one yourself. To be faster, I will use the existing image. If not, it will, as I was saying, take it from Docker Hub or build it locally. And then at the end, what it does is to launch, as I was saying, here in the browser, the notebook. If not, in case something fails, or if you want to make this connection remotely, you can take this token and open it by yourself. Just a quick thing by running. Is it running? Okay, it's taking some. Okay. I will not train it because here in my laptop it takes a lot of time, but I just want to show you the widgets. Okay, I will continue running here. So here Similarly, if you have used Zero Cost or some Google Colab widgets, you will have this that you just need to put the paths to your training data, the images, the labels. Then where do you want to save your results? Here. This is something important. My super good unit. Only the things that are inside the result folder will be saved. Everything else will be lost. Similar to Colab, like if you save it in your Google Drive, it's safe. If not, it's lost. And then yeah, well, I'm not going to train it, but if so, it will be like 10 epochs, and I will keep everything the same. Load and run, and yeah, here it will create the patches. And yeah, we can see here an example, and you can continue running the notebook to show the training, but I think that I'm a little bit tight with the time, so we will go back to the presentation. Wait, yes. So at the end, what deep learning for Make Everywhere from the developer's point of view is to try to give your notebook in a reproducible way for other users, but from the user's perspective, what you get is a collection of user-friendly deep learning models that you can train, test, and use. And yeah, you have all the notebooks from Zero Cost available, some custom models from Deepbacks, notebooks, sorry, from Deepbacks, and everything is really well connected to the Bioimage model too, so that you can export your models also, if the notebooks has that feature, to the Bioimage model too, or you can take them from as tools. So at the end, as a summary, Deep Learning for Make Everywhere brings reproducible, transferable, and transparent pipelines, which are notebooks using containers. It brings long-term reproducibility and is a centralized platform that allows to disseminate your pipelines. Finally, I wanted to thank all the people that help in this project, in Deep Learning for Make Everywhere, and yeah, acknowledge my previous group in Ricardo Enriquez, my new group in in Turku, the Cell Migration JackMed Lab. And yeah, and if you have any question, I'm happy to answer them.